Okay, here's our penultimate example problem, right? Second to last problem we have, and it's about a charged rod that has positive charge distributed throughout the volume. Why don't you take a moment and, if you want to, find where you can print out a copy of this file and read through all the parts A through D. This is a 2-page document. And once you've read through all of it, then you can unpause and resume the video. Okay, so let's take it from part A. We're told that the charge is distributed with, what do they say? The charge distribution is cylindrically symmetric, and the total charge per unit length is given as lambda. So we're asked to use Gauss's law to find an expression for the electric field at points outside of the rod. So let's go ahead and pick an appropriate Gaussian surface. If we want to find the electric field, for example, at this point P, then a Gaussian surface that passes through that point and is also cylindrical will suffice, as long as lowercase l, the length of our Gaussian surface, is significantly less than the total length of the rod. In fact, you can see from the squiggly line, the rod would extend even farther, but it's been cut off here. So whatever it is, it's got a total length of capital L and a total charge of Q. And in fact, lambda is Q over capital L, but lambda is also the amount of charge inside of that Gaussian surface divided by lowercase l. So we're going to take advantage of those two expressions being equal as part of our solution. So step 1, state Gauss's law. The integral of E dot dA is the amount of charge inside the Gaussian surface divided by epsilon naught. And keep in mind that this Gaussian surface is totally enclosed. There's not just surface area on the side walls. Think of it like a soup can. It doesn't just have the label, it also has the lids. But the one thing we note is no electric field lines pass through the lids, right? The electric field only passes through the label. And so this expression on the left side of the equation for total flux, there's no contribution to the total flux through the caps of our Gaussian surface. So we can skip a couple steps and recognize that the left side is just going to become E times the area of our Gaussian surface through which there is flux. And if you imagine that this really is like a soup can label, and we cut along this dotted line I'm drawing, let me highlight that. Hopefully you'll see this dotted line I made. If we cut that and then unrolled the label of the soup can, it would be a rectangle with area 2 pi r times L, right? Okay, and then the right side of the equation, Q in, well, because Q in over lowercase l is the same thing as Q over capital L, or if we want, we can just say Q in over L is lambda, then Q in is lambda times lowercase l. So if we had chosen just a slightly longer Gaussian surface, that would still work. L would be bigger, but it would be bigger on both sides of the equation, so it cancels out. So E is equal to 1 over 2 pi epsilon naught times lambda over r. Or you might prefer to write that as 2k lambda over r. Same thing, knowing, of course, that k is 1 over 4 pi epsilon naught. These two circles both represent a cross-sectional view of the rod. So with our eyes, looking this way, we see the cross-section, and we have to draw several equipotential lines in the region outside So let's draw the equipotential lines in red. There's one. There's another one. And there's another. They're concentric circles. The spacing in them is not uniform, but they are concentric. So if this is a positive charge, and it is, and there's our highest electric potential. Out of the three I've drawn, there's the lowest electric potential. Here would be some intermediate value of electric potential. Draw several electric field lines. And that's easy enough. Let's draw the field lines in purple. How's that? In this cross-sectional view, they just point radially outward. And we note, if the two of these were to overlap, that the electric field lines will cross the lines of equipotential at 90 degrees at all points. Okay, on to part C. So this point C is at a distance A from the center of the rod. In other words, it's on the surface. Point D is well outside of the surface at a distance of 3A. So we have to determine the potential difference between point D and the surface. All right. V is a symbol for electric potential. Delta V is a symbol for potential difference. So VC minus VD is equal to negative the integral from D to C of E out dot dr. Or in other words, this delta V is equal to positive the integral from C to D of E out, which we derived in part A, lambda over 2 pi epsilon naught times 1 over r dr. Now what we really mean by C is from A, what we mean by D is 3A. Okay, so delta V is equal to lambda over 2 pi epsilon naught times the integral from A to 3A of r to the negative 1 dr, which gives us natural log of r, and we're evaluating it from A to 3A. Well, the natural log of 3A minus the natural log of A is the same thing as the natural log of 3A over A, and then the A cancels out. So we get delta V is equal to lambda over 2 pi epsilon naught times the natural log of 3. So there's a uniform charge density in terms of the linear charge density. If I were to take a slice of this charged rod and I compare it to another slice of the same thickness, which one of those slices has a greater number of coulombs? They're the same. We were told that lambda is constant or uniform, right? So the number of coulombs per meter is a constant. But now we're told, as far as the way the charge is distributed from the center, from r equals 0, out to the surface at a distance of A, that the charge is not distributed uniformly. In fact, it's given by this formula, the volume charge density is equal to rho naught times the quantity r over a to the 1/2 power. So we have to determine the electric field as a function of r for points inside. So I already know E out is lambda over 2 pi epsilon naught times 1 over r. So this part of the problem is asking us what the heck is E in. So we're going to make another Gaussian surface. So if we want, we can picture the end view of this. So we're going to make a Gaussian surface here, or if we draw the side view, a Gaussian surface like that. Again, our Gaussian surface has a length lowercase l, whereas the whole rod has a length of capital L. So, as always, we start with a statement of Gauss's law. The integral of E dot dA is equal to Qn over epsilon naught. E times 2 pi r lowercase l is equal to the integral of rho dV over epsilon naught. Now in place of rho, we can put in this formula that we're given. Rho naught r over a to the 1/2 power. Don't forget our 1 over epsilon naught. Okay, so that substitutes for rho. We need to substitute for dV. The volume, if we just start building up cylindrical shells, we know the volume of this cylinder would be equal to pi r squared. That's the surface area of the end caps of our Gaussian surface, right? Pi r squared times L. So dV dr is 2 pi rl. So dV can be substituted with 2 pi rl dr. So E times 2 pi r lowercase l is equal to rho naught over epsilon naught, the integral r over a to the 1/2 power times 2 pi r l dr. Now the 2 pi and l would all be constants that we'd pull out of the integral, so we can cancel those. So E in is equal to rho naught over epsilon naught. Let's pull out the a to the 1/2 power as well. So now we've got an r to the 1/2 and an r to the first, so that's r to the 3/2 power total. And then we're still left with a dr. Oh, and we're integrating from 0 up to lowercase r. Okay, so the integral of r to the 3/2, we think of integration as the antiderivative, so we know we're going to get an r to the 5/2. And I guess we've got to put a 2/5 in front of that. If we evaluate it from 0 to lowercase r, that doesn't change anything, right? So E in is equal to rho naught over epsilon naught a to the 1/2 power times 2/5 r to the 5/2 power. Let's tidy that up a little bit. And that looks good enough to me. Okay, well there we have it. One more example problem to go.